I would like you to meet this very nice matrix. It's a very nice matrix. You know, it's just ones and minus ones. So I think this is very nice and very cool. How do we find the inverse of this? Well, we utilize the augmented matrix construction. We start by appending / gluing / augmenting the identity matrix to this matrix, and we proceed by turning this into the identity matrix, you could say. So we want to make this an identity matrix, which means we want this to be the pivot. We want to make zeros here, 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 and here. And we want the ones on the diagonal as always. As usual, we proceed column by column, and we will proceed with normal row operations. I'll take this row, I'll add it to the second row. I'll take the same row and I'll add the negative counterpart of it to the third row. The goal is to make zeros. And I'll now summon my nice draft. I have a draft for Gaussian elimination procedures, so not to get confused. So as intended, this should give me 2 zeros here. It will give me some unknown values here, which I need to compute, and I will use my nice table for that very specific purpose. I multiply by 1, that's not too difficult. I get 1 minus 1, 1, 1, 0, and 0. I'm adding this to the second row, which says minus 1, 1, 1, 0, 1, 0. This would give me 0, 1, 1, 2, 0, 0, 0, 2, 1, 1, 0. This is just minus 1. So I multiply all the elements by minus 1. And now I write the other row, which is 0, 0, 1 here, and 3 ones down below. 0, 2, 0, minus 1, 0, 1. I hope this is not too difficult. This is great. I do not have my 1 on the diagonal here, but I can still use this as a pivot and then switch the rows later on. This is already 0, so I'm very lucky to have this. I would like to now cancel out this minus 1, make it a 0. So I'll multiply the third row by a positive half. Will give me 1, and this will in turn cancel out my negative 1. As usual, the part on the left does not get affected because you're multiplying things by 0, and multiplying things by 0 just gives you 0. This is the row that will change. And my row is this one. I multiplied by a half. And I added to the first row. which gives me this. Perhaps, no, I think it is fine. This is a 2, yes, but I can divide by 2 later. I'll do it later. So now I have my second pivot. I just need to have a third pivot here. And this is even more amazing because I have a 0 here. Then all I need to do is just to have another 0 there and I'm done. How do I make a 0 there? I take the second, I take the second row, which has my intended pivot, and I scale by a -half. When I do this, the 1 should cancel out and become a 0. I'm really using up all of my space here. Yes. So here you're scaling the -half by 0, so they stay intact. And here you make it 0 by design. You just need to compute the other 3 values. But let's double check this. So you have 0, 0, 2, 1, 1, 0, and you scale this by a -half. So you get 0, 0, -1. I'm adding this to the first row. Which will give me yes, exactly. So 1, 0, 0, 0 -half, and a half. Now finally, well, almost. Yeah, so we're almost there. I just need to do 2 things. The first thing is I need to switch this row for that row, and I would like to multiply this by a half, and multiply that by a half. The whole row, I mean. So this will give me, first off, switch the rows, and then multiply by a half. This gives you 1, half, half, 0, -half, 0, and a half. Don't forget this line here. And now that we have the equivalent of the identity matrix on the left, then with great confidence we can say that if this is the matrix A, then our matrix A inverse is going to be precisely given by the values which are right here. Yes, so the values are correct. I'm very happy with this. And this is the answer for the exercise. I would say it's pretty straightforward and pretty nice. But always keep in mind that not every matrix has an inverse. In fact, there are a lot of matrices which do not have inverses. There are multiple ways to check this. The first one is usually when the Gaussian elimination process fails and you get, for example, a block of zeros where you don't get, I should do like this. You don't get the pivot. No, yes, you don't get the pivot that you would like to have. I'm sorry, it's because the camera is mirrored. You don't get the pivot that you want to have, and then you realize, okay, this is not going to work. Another way to check, quickly check that the matrix is linearly independent in terms of its rows is to compute the determinant. And the final way is to do this is to give it a good look. This is not a good strategy because sometimes it is very well hidden. It doesn't have to be the addition of two rows that gives you a third row. It could be a twisting combination of the two that gives you a third one, and you don't really notice that. Let's say, for example, a third row vector is in the span of the other two. So I would say the determinant test is a very good test for that. If you compute the determinant, I think it will be non-zero. And one thing I noticed about this matrix is that it is symmetric. If you take the transpose of this matrix, it's equal to itself. Isn't that cool?